So after simple cubic unit cells crystal structure, today we will cover the body centered cubic crystal structure. So it is one of the most common ways for the atoms to arrange themselves in a metals. The body centered cubic structure is based on the previous lattice of the same name with one atom per lattice point at each corner of the cube. And the center of cube. So the body centered cubic is nearly a closed packed and has a greater stability as compared to simple. And the reason why they are most stable or great stable because they have high number of nearest neighbors and next nearest neighbors. So the body centered cubic cell belong to space group 2 to 9. Okay. So it is imagined as a cube with an atom on each corner, an atom in the cube center, and it is one of the most common structure for the metals. Most metals generally have a body centered cubic as a crystal structure. Okay, so this the body centered cubic has two atoms per unit cell, and the lattice constant is 4r by root 3, and their coordination number is 8, and the atomic packing factor is 68%. Okay, so later we will discuss what are the examples of body centered cubic materials. So as we know that the BCC is one of the most common crystal structures, there are many examples. Okay, for example, lithium, sodium, potassium, chromium, iron, cesium, barium, and tungsten. All of these have BCC as a crystal structure, and the list is not limited; it can be beyond that also. So BCC metals have ductile to brittle transformation temperature, which means they are brittle at a lower temperature and ductile at a higher temperature. So some BCC metals are ductile at a room temperature and others are brittle. Generally, these BCC metals also tend to have a high melting point because they have a large number of nearest neighbors and the next nearest neighbors, which was also the reason behind their stability. Later we will discuss their coordination number. As we already know, their coordination number is 8, and that is not the maximum. Okay, because in a closed pack structure it is about 12, but the BCC has such a high stability because of its neighbor and next to next neighbors. Okay, so there are 6 next nearest neighbors, but these are only 15% farther away than the nearest neighbors. In some sense, this allows the BCC crystal to act as though they have the 14 bonds, which is higher than the maximum of 12. So this may be one of the reason why they have the higher melting point. Okay. So the nearest neighbor distance is about 2r, and the next nearest neighbor distance is 4 by root 3r. Okay. So next point about their packing factor. As we have already discussed about its packing factor, it is about 68%. Okay. Then interstitial sites in the body centered cubic. These are the spaces inside a crystal where another kind of atom could fit. Okay, so BCC has 6 octahedral sites, which means that a small interstitial atoms could fit in 6 positions such that it is equally surrounded by the 6 FCC lattice atoms. Okay, so BCC also has 12 tetrahedral sites, which means that a small interstitial atom could fit in 12 positions such that it is equally surrounded by 4 FCC lattice atoms. So finally, it is extremely common in metals. and therefore its result in the interesting properties like ductile to brittle transformation temperature. It has high melting point and atomic packing factor as a 68%, and many of its property arise because the next nearest neighbors bond nearly as powerful as the nearest neighbors. Okay, so this was the introduction about or the whole